Welcome to my lecture about matrices. The following are the topics that we will cover in this lecture. First, we will define what a matrix is, what are the different types of matrices, how do we perform matrix addition, scalar multiplication, matrix multiplication, and what is a matrix transpose. An M by N matrix A is a rectangular array of numbers that are arranged in M rows and M columns. So we write matrix A as an array containing M rows and M columns of elements. We shall denote the elements of the matrix as A sub 1 1, A sub 1 2, A sub 1 n for the first row, a sub 2 1, a sub 2 2, up to a sub 2n for the second row, and so on and so forth, up to the nth row, a sub m1, a sub m2, up to a sub mn. We can also write matrix A as A equal to aij that is bracketed, where I is the row that ranges from 1 to m, and j is the column that ranges from 1 to n. The symbol aij refers to any element of A. Element aij is the element found at the intersection of the ith row and j column. So this is the ith row and this is the j column. This will be the element aij. So A sub 21 refers to the element found in the second row and first column of matrix A. A sub 31 is the element at the intersection of row 3 and column 1. A sub 1 3 is the element at the intersection of row 1 column 3. Take note that aij is not equal to aji. So the first subscript refers to the row and the second subscript refers to the column. The elements of the ith row are a sub i1, a sub i2 up to a sub in. As a row matrix, we can write this as open bracket a sub i1, a sub i2 up to a sub in close bracket. On the other hand, the elements of the jth column are a sub 1j, a sub 2j, a sub 3j up to a sub mj. As a matrix, we can write this as open bracket a sub 1j, a sub j up to a sub mj. For the elements of the ith row, observe that all the first subscripts are I, indicating that all the elements come from the ith row. And as for the elements of the jth column, observe that the second subscript are all j, indicating that all come from the jth column. The following are some examples of matrices. Matrix A is a 2 by 3 matrix, meaning there are 2 rows and 3 columns. Matrix B is a 3 by 3 matrix. Matrix C is also a 3 by 3 matrix. Matrix D is a 4 by 2 matrix having 4 rows and 2 columns. Matrix E, on the other hand, is a 2 by 2 matrix, and matrix J is a 4 by 4 matrix. We now define a square matrix. An M by N matrix A is a square matrix if and only if M is equal to N. That means that the number of rows and the number of columns are equal. So we can write matrix A as an N by N matrix. Example, matrix A with elements 1, 0, 2, -1 is a square matrix having 2 rows and 2 columns. Another is matrix B with elements 1, 0, 0, 0, 1, 0, 0, 0, 1. So matrix B is a 3 by 3 matrix. Two matrices are said to be equal if and only if Aij is equal to Bij for all the i's and for all the j's. So matrix A, B, C, D, E, and F, and matrix B with elements 3, -1, 0, 5, 3, -2 are said to be equal if and only if the corresponding elements are equal, meaning A is equal to 3, B is equal to -1, C is equal to 0, D is equal to 5, E is equal to 3, and F is equal to -2. So A is equal to B if and only if A is 3, B is -1, C is 0, D is 5, E is equal to 3, and F is equal to -2. An M by N matrix O is called a zero matrix if and only if Aij is equal to 0 for all the i's and for all the j's. So, simply put, matrix O or matrix 0 is a matrix where all elements are 0. So say for example, the 0 matrix 2 by 3 contains 2 rows and 3 columns of zeros. So Aij is equal to 0 for all rows and for all columns. Next, a diagonal matrix. A diagonal matrix A is a square matrix if and only if Aij is 0 for all i's not equal to j. So that means that the elements are all 0 except for those found along the main diagonal. Say for example, A is a 3 by 3 matrix. All elements are 0 except for those along the main diagonal. So Aij is 0 for all i's not equal to j. Here we have the element A, 1, 2, first row, second column. 1 and 2 are not equal. This 0 is the element A1, 3. The row is row 1 and the column is column 3. 1 and 3 are not equal. So it's only those elements in the main diagonal where Aij or where I and j are equal and which are not all equal to 0. So for this 3 by 3 matrix, the elements along the main diagonal are A11, A22, and A23. 3, 3, I and j are equal, and all of them are not all 0. Now, a scalar matrix, on the other hand, is a diagonal matrix with the added condition that elements along the main diagonal are all equal. Say, for example, B 3 0 0 0 3 0 0 0 3. All elements are 0. All elements are 0 except for those along the main diagonal. So it's called a scalar matrix. An n by n matrix A is called an upper triangular matrix if and only if aij is 0 for all i's greater than j. So supposing that A is a 3 by 3 matrix, the elements are A11, A12, A13, A21, A22, A23, A31, A32, and A33. We examine all the subscripts, the aij's, and select those where I is greater than j, where the row number is greater than the column number. So 2 1, the row number is 2 and the column number is 1, and 2 is greater than 1. Okay, how about A31? The row number is 3 and the column number is 1. Same with A32 and nothing else. Okay, so that means that all these elements must be 0. So say A is equal to 4 0 1 0 1 3 0 0 and say negative 2. As you observe, elements are actually found, the non-zero elements, not all zeros, are found along the main diagonal and above the main diagonal. All the rest are zeros. So it's an upper triangular matrix. Now for a lower triangular matrix, it will be the other way around. Aij is 0 for all the i's that are greater than j. For all the i's, or rather for all the i's less than j. So these are actually the elements A12, A13, and A23. So say for example 4 0 0 1 2 0 negative 1 negative 1 and 1. So the elements along the main diagonal and down below are not all 0. All the rest are zeros. We now define matrix addition. If A is equal to Aij and B equal to Bij, where both A and B are m by n matrices, the sum of these matrices A and B is another m by n matrix C equal to Cij, defined by Cij equal to Aij plus Bij for I from 1 to m and for j from 1 to n. Say for example, A is A11, A12 up to A1n, A21, A22 up to A2n, down to AM1, AM2 up to AMN. We then add this to matrix B, where the elements are B11, B12 up to B1n, B21, B22 up to B2N, down to BM1, BM2, up to BMN. So if you want to find the sum of these two matrices, what do? We just add the elements correspondingly. So that will be A11 plus B11, A12 plus B12, up to A1N plus B1N. So we do that for all elements of A and B down to the last row, AM1 plus PM1, AM2 plus PM2, up to AMN plus BMN. So we just add the elements correspondingly. Let us take on the following example. A manufacturer of a certain product makes three models, A, B, and C. Each model is partially made in factory F1 in Taiwan and then finished in factory F2 in the United States. The total cost of each product consists of the manufacturing cost and the shipping cost. The cost at each factory in dollars can be described by the 3x2 matrices F1 and F2. So factor 1 in Taiwan, the manufacturing cost and the shipping cost for models A, B, and C are 32, 40, 50, 80, and 70, 20. And these data are represented as a 3x2 matrix. So for factor 2 in the United States, we have the manufacturing cost and the shipping cost for models A, B, and C, also represented by a 3x2 matrix. So we write a matrix, or write in matrix form, the total manufacturing cost and total shipping cost for each model. In other words, we simply have to add the manufacturing cost and the shipping cost for models A, B, and C for both factories F1 and F2. So what we do is we simply write or get the sum of F1 and F2. So that will be 32, 40, 50, 80, 70, and 20 plus 40, 60, 50, 50, 130, and 20. So both are 3x2 matrices, and the sum will also be a 3x2 matrix. So 32 and 40 will give us 72, 40 and 60 is 100, 50 and 50 is 100, 80 and 50 is 130, 70 and 130 is 200, and finally 20 plus 20 will be 40. So the total manufacturing cost for model A is 72, for model B is 100, and for model C is 200. The total shipping cost for models A, B, and C will be 100, 130, and 40 respectively. Scalar multiplication. If A equal to Aij is an m by n matrix and R is any real number, then the scalar multiple of A by R, denoted by Ra, is the m by n matrix B equal to Bij, where Bij is equal to Raij for I from 1 to m and for j from 1 to n. In other words, the resulting matrix will also be of the same size as A, and each element of A is multiplied by the constant R. Say for example, our A is the 3 by 2 matrix: 1, 4, negative 2, 1, 0, and 3. And R is a constant equal to negative 2. So RA is equal to negative 2 times the matrix 1, 4, negative 2, 1, 0, 3 equal to negative 2 times 1. That would be equal to negative 2, negative 2 times 4. That will be negative 8. Negative 2 times negative 2 is positive 4. Negative 2 times 1 is negative 2. Negative 2 times 0 is 0. And finally, negative 2 times 3 is negative 6. If A and B are m by n matrices, we write A plus the negative 1 multiple of B as A minus B. We call this as the difference of A and B. So, matrix subtraction is actually addition of matrix A and the negative of B. So all elements of B are multiplied by negative 1 and added to A. So say for example, A is a 2 by 2 matrix, 1, negative 3, 4, and 2. And B is another 2 by 2 matrix, negative 3, 1, negative 2, and negative 4. So to find the difference, A minus B, is to simply multiply all elements of B by negative 1 and add it to A. Or we simply apply ordinary subtraction. 1 minus negative 3, 1 minus negative 3 will give us positive 4. Negative 3 minus 1 is negative 4. 4 minus negative 2 is 6. And 2 minus negative 4 is also 6. If A sub 1, A sub 2, and A sub n are m by n matrices, and C sub 1, C sub 2 up to C sub k are real numbers, the expression of the form C sub 1 A1 plus C sub 2 A2 plus and so on and so forth plus C sub k times A sub k is called a linear combination of the matrices A1, A2, and An. And C1, C2, Ck are called the coefficients. Let us now define the transpose of a matrix. If A equal to Aij is an m by n matrix, then the n by m matrix A sub t equal to Aij sub t, where Aij sub t is equal to Aj for I from 1 to n and j from 1 to m. So if A is an m by n matrix, the transpose of matrix A sub t, is an n by m matrix, where the element Aij of the transpose is equal to Aji of matrix A. So suppose we have matrix A, which is a 2 by 3 matrix. The transpose of matrix A, or A raised to T, is a 3 by 2 matrix. So A is a 2 by 3, and the transpose is a 3 by 2 matrix. The row elements of A becomes the column elements of AT. So the first row of A becomes the first column of AT. So 3, negative 4, and 1. The second row of A becomes the second column of A transpose. 5, 0, negative 2. So we simply interchange the rows and the columns. The row of A becomes the column of A transpose. Matrix multiplication. If A equal to Aij is an M by P matrix, and matrix B equal to Bij is a P by N matrix, observe that the number of columns of matrix A, which is P, is equal to the number of rows of matrix B. The product of A and B, denoted by AB, is an M by N matrix C equal to Cij, defined by Cij equal to AI1 times B1j plus AI2 B2j plus and so on and so forth plus A sub IP times B sub Pj. In a more compact form, that is equal to the summation of A sub ik, B sub kj, where k is from 1 to p. I ranges from 1 to n, and j from 1 to m. Alright, so to find the element Cij of the resulting matrix, what we do is we multiply the elements of the ith row of A correspondingly to the elements of column J of B. So if you want to find the element C1, 2, the elements of row 1 of A is multiplied correspondingly to the elements of column 2 of B. So we do that for all i's from 1 to n and for all j's from 1 to m. For a better understanding about matrix multiplication, supposing that we have matrix A equal to a 2 by 3 matrix, 1, 3, negative 2, 0, 1, and negative 1. And B is a 3 by 2 matrix. So B is a 3 by 2, 1, negative 2, 0, 1, 3, and 4. 3 by 2. So the requirement is that the number of columns of A must be equal to the number of rows of B. And the resulting matrix AB will be of size 2 by 2. Okay? So the size of the product will be the number of rows of A, which is 2, and the number of columns of B, which is also 2. Alright. So the product AB is equal to, let us rewrite the elements, 1, 3, negative 2, 0, 1, negative 1, and 1, negative 2, 0, 1, 3, 4. Okay, so the resulting matrix is a 2 by 2 matrix. It's a 2 by 2. Start with the first row. The first row of A is multiplied to the first column of B. So 1, 3, negative 2 is multiplied or are multiplied correspondingly to 1, 0, and 3, and we get the sum. So that will be 1 times 1 is 1, 3 times 0 is 0, and negative 2 times 3 is negative 6. Then we go to the second column of B. 1 times negative 2 is negative 2, 3 times 1 is 3, and negative 2 times 4 is negative 8. Since we are already done with the first row of A, we go to the second row. The second row of A, 0, 1, negative 1, is multiplied to each and every column of B. So 0 times 1 is 0, 1 times 0 is 0, and negative 1 times 3 is negative 3. Finally, second row of A to the second column of B. 0 times negative 2 is 0, 1 times 1 is 1, and negative 1 times 4 is negative 4. So the product will be 1, 0, negative 6 is negative 5. Negative 2, 3, and negative 8 will be negative 7. 0 and 0 and negative 3 is negative 3. And 0 plus 1 minus 4 is negative 3. So, in matrix multiplication, we start with the first row of A multiplied to each and every column of B. So, all the products are added together. So, first row of A, first column of B, the resulting sum will be the element C11. The second element of the first row will be the product of, or the sum of the products of the first row of A and the second column of B. So you start with the first row, multiply it correspondingly to the elements of the first, second, up to the last column of B. Once you are done with that, you proceed to the next row of A. Again, multiply the elements correspondingly to each and every column of B, thus generating the elements of the second row of the resulting matrix. We do that for all the rows of A, multiplied to all columns of B to generate the elements of the last row of the resulting product. You may try this one. Say we are given A equal to 4, negative 1, 0, 1, negative 2, negative 2, 3, 0, and negative 4. Another 3 by 3 matrix B, negative 2, 1, 3, 0, negative 2, negative 1, 1, 3, and 4. Find the product AB, BA, and C if the two will be equal. You also determine the product of A and A transpose. Thank you for listening to my lecture.